Okay, recording started. Hello everyone, my name is Abhishek, and I have given introduction a lot of time. So I will get with the start with the workshop right away. So this workshop is on fundamentals of CFD, and from that we'll transition to the basics of OpenFOAM, the structure of OpenFOAM. So what I will do here is I'll try to speak slowly, and I want you to try everything or practice everything me parallel with me as it is as it is possible, as far as it is possible. And if you are lagging behind, you can stop me anywhere in the moment. I'll stop and repeat everything that I've said earlier, so don't hesitate to stop me if you're feeling trouble anywhere. If your system is, if you're not able to catch up, just raise your hand or just speak. So we'll start with the workshop. So first of all, what I want to do is first will teach you basics of. So I am using Ubuntu in VirtualBox because I am familiar more with it and I am comfortable with it. So first of all, what we will learn is, as you most of you are beginner to OpenFOAM and Linux commands. So first of all, we'll understand some of the basic Linux commands which are important in OpenFOAM. Okay. So first, let me tell you this, that I've installed OpenFOAM here in the root. So my OpenFOAM is located in this OPT in computer in the root folder. In OPT, OpenFOAM 9 is there. Paraview is there. VirtualBox is also there. So see OpenFOAM, my OpenFOAM installed in the root. You should also have the idea where your OpenFOAM is installed. Okay. So first you should have idea where your OpenFOAM is installed. Now you can either press Control Alt T, that will open the terminal for you, or either you can.
Can you please share the screen actually?
Share screen.
Right. Okay. Sorry for that. Actually, I shared earlier. I forgot. I'm sharing it right now. Is it visible now?
Yes.
Yes.
Okay, so this is VirtualBox. Ubuntu in VirtualBox I have installed in my laptop, which is Windows-based system. So my OpenFOAM is installed in here in root folder. So this is home folder, right? This is home in Ubuntu, and this is root where my OpenFOAM is installed inside OPT. In OPT, I have Paraview also, VirtualBox folder also, and here is OpenFOAM. So this is where my OpenFOAM is installed. So first of all, you should have the idea where my OpenFOAM is installed, right? Then you can do Control Alt T to open the shell, a terminal. Okay, or if you are not familiar with these things, you can do right click or anywhere, and it will open that location for you. So right click, do open in terminal. Okay. So first of all, what we will teach you is env command. So I think just raise your hands if you don't know the basics of Linux commands such as cd, pwd, or ls commands, things like this. So you guys know cd, pwd command? You don't know? Okay. All right. So in Ubuntu or Linux based system, in Windows you go like this. You open OpenFOAM, you see the folders, right? But it is not like this in Linux based systems such as Ubuntu or CentOS. There are a lot of other Linux based system as well. So most of us use OpenFOAM. Okay, so when you do ls command here, you can see we are at home.
Can you zoom your terminal? So just
I'm doing okay.
Plus Control and plus. Yes.
Okay, so I'll keep this short so you can see the background of the screen also. You can see at the background we have desktop, documents, downloads. When we do ls command, it is showing us everything, right? It is showing all the folders that are there. Then when we do pwd, so it is showing us the address of the present directory, that is present working directory. Okay, that is home, Abhishek. Okay. So now if you want to go inside this folder, this OpenFOAM folder, this one, then we do CD. Okay. And then we press O and then you do tab. It will automatically recognize because there is only one folder starting with O. We can go inside O, OpenFOAM. Now you are inside OpenFOAM now in the terminal. Now you want to see what is inside OpenFOAM, then you do ls. All right. So inside you have folder Abhishek 9, and there is run folder as well. Okay. Now you want to, you can try this like if this, you can try all these things.
Try to go
Now,
little slow.
okay, okay,
So speed is slightly faster.
okay. So if you want to go inside another folder, whichever folder you have opened, you can do like similar, that is CD. And I know I'm going into Abhishek 9, you can go into any another folder. So try these commands, ls, pwd, that is present working directory, cd, current directory, or cd is something else, but I think Pratyush cd stands for
Change directory.
change directory. Yes, yes, change directory, and try to run these commands. Okay. Now we'll move on to another command. So later, when we'll use a lot of commands, we'll teach you that at that time. One of the most important thing is to use upper arrow. So you see, we have given right now the commands like this cd, Abhishek, ls, OpenFOAM, pwd. Now use upper arrow. It will show you all the commands that you have given in like previously in this terminal or in any terminal. Use arrow. Okay. Use upper or lower arrow both. It will change. It will directly show you the command. You don't need to remember any of these commands. It will come by default. Now I am inside. I think this much is clear. Raise your hand. Give me something to move ahead. Okay. I hope you are there. So next important command is cd only. When you type cd without, if you want to go to the back folder, then you do cd space dot dot. Cd space dot dot, it will go to the previous directory. And if you type only cd, then it will go to the home directory. So no matter where you are, let's say you are in any another folder. Okay. If you want to go to the home, you type cd. These are the basic commands, and you can always use upper and lower arrows. Okay, to see which command you previously entered. So next is, I think this much is done. I'll now move forward with the OpenFOAM things. Okay. The next important command is env. You see, when I typed env, it showed me a lot of commands. So environment, these are like shortcuts to shortcut pathways or shortcut commands to run any code or like give any input to the terminal. Okay, so these are environmental variables that are like already they are already there in the shell. Okay, so how do these work? So how do these work? Okay, so now these are not, most of them are of no use to you. So the only command that are used to you are of OpenFOAM environment. What are the already previously installed OpenFOAM environment? that you'll use a lot of time. So for that, you have to use this command, that is environment grep form this. Okay. So when you enter this, now you can see the commands like form settings, form MPI, form run, form exit libin. All these form tutorials will take you to the form tutorials. So now how these commands work is, so they basically these are environmental variables for this Ubuntu system. We start with the name OpenFOAM. Okay, form. So let's go here. So this form run variable is the address of this directory. Okay. So if you have not already made this form run directory, so what you should do is you should type this form run and just enter. The terminal will say to you that this form Abhishek, open form Abhishek 9 run is a directory. If terminal is if you are, because it is already, this is a like folder. This run is a folder. This is a directory. So if it is showing in your case that there is no such directory and it is showing you some address, then you have to do this. Because this is the directory where we will run each and every case in your open form. Every simulation that you want to do, you will not do it in open form folder. You will do it here. Okay. So what you have to do is you have to do mkdir form run. This means is mkdir means make directory. It is like creating a new folder. Okay. So when you do this new folder, it is the same thing. But here you are doing this using terminal. I hope this is clear. If your terminal is showing you this thing that there is no such directory, okay, then you have to make a directory using this command. Now what you will do is you will go to the run folder. I'm typing run only. When you just simply type run, it will go to the this folder. That is this form run directory. This is where we will run each and every case of OpenFOAM, not in the OpenFOAM main folder. So you know the OpenFOAM main folder is this one. This is the main folder of OpenFOAM, which I showed you initially. This form tutorial environment is go to the tutorials. Okay. This much is done, I think. So what we will do now is we'll run a sample case for you. We'll just run a basic simulation in OpenFOAM so that you have an idea like how the simulation runs in OpenFOAM and how do we, what is like unlike ANSYS or other softwares which are GUI based, how it is in OpenFOAM. So to show you this, what we will do is we'll copy any case. There are like cases in OpenFOAM. We'll copy any case and then try to run it. We'll copy that case to run folder. So that you can do using this CP. CP means copy, and -R means copy the directory. Okay, so my OpenFOAM is installed in OPT. So you have to go to CP -R, OPT OpenFOAM tutorials, incompressible, icofoam, and then cavity, or you can use tab, you can use elbow, just copy cavity. So you'll copy this cavity folder to dot where your run folder. So if you want to copy some specific, this cp -r is the command. This is the like which folder you want to copy, and this is the destination folder. I want to copy this in the run itself. Please see this command. Or if you are not familiar with this, because I myself when I started was not good at this. So instead of doing this, you can do this. So my OpenFOAM is here. You have to go to OpenFOAM tutorials. Uh, then in tutorials, we want to go for incompressible flow. In that, this particular solver, cavity here. I want to copy this to my run folder. Where is my run folder? My run folder is this, which where it is OpenFOAM Abhishek 9 and run. This is my run folder. Okay. So I can paste it here, but I will not do that. What I will do is I'll just from terminal, I will run this command, and you can see now an extra folder copy is here, a cavity is here. You could have also done this using this paste as well, but we are doing this from the terminal. It's the same thing. Everyone, please raise your hand if you are have reached till this moment. If you are lagging behind, just let me know.
Hello. I
Yes.
have a small doubt actually. Like you
Mm-hmm.
created Abhishek 9 folder other than that make
Yes.
directory
Okay.
form
No,
run.
no, I didn't created it. Okay, so you don't have this Abhishek 9 folder.
Yes. How could I?
Okay,
How should
so
I?
yeah. So I'll tell you. So I'll, similar to these form environmental variables in this bash or this Ubuntu, we also have form environmental variables starting with. So you don't need to type your command. I will also not type. So what we will do is we'll do this upper arrow use and we'll read this command. So instead of form, now you have to do what? WM. Okay.
Okay.
Environment web WM. So when I enter this, you see a lot of environmental variable with this. Okay.
Okay.
So here you can see WM project directory is OpenFOAM. Okay.
Okay.
So when you and so what you have to do is you have to create a project user directory.
Hmm.
So
Okay.
what you do is MK. So there should be one user directory. One second. Yeah, here it is now. So you can see WM. So the thing is this WM project specifies to the OpenFOAM environment, which is at the root. But you don't want to run any simulation in your OpenFOAM folders. You want to run it outside. So for
Yes.
that, this is the directory that you have to use. So when you type this WM project user dir, okay. So it will show you this is a directory.
Okay.
If you have not already made it, it will show you this address and it will tell you is not a directory. Is it
Okay.
showing you that? Just
Uh, uh,
type this command.
okay.
Yeah.
Okay. I'm just typing. Okay. Give me a second.
Am I showing you no such file or directory here when I type this WM project user directory?
It is showing you that, but it is also show you this address.
Yes, it's showing.
Something it is not showing you at all.
No, it's showing the address.
Okay, so what you have to do is you have to make directory. Okay. But if you have this done this mkdir form this command, sorry. But if you have given this command, that is make directory form run, then it should make this Abhishek 9 as well. Have you
No,
given this command?
when I given that command, it's showing that cannot create directory. Make there cannot create directory. It's showing.
Okay, so what you have to do is you have to do this. So, a second. So you have in front of this, you have to write this mkdir wm project user directory.
Okay, just me try. Let me try.
In my case, it is showing that it is a directory. Is a directory.
Is
Like
a directory means this directory is already there.
okay, then how should I go into that particular folder actually? Because in your case, after that virtual box, you have that path OpenFOAM Abhishek, and how should I go to that?
So
And also
type cd and
okay,
this path.
okay, then okay.
And in like if you are not familiar with these things, then you can always go through this. Like this is showing me home Abhishek open form Abhishek 9, right?
Yes,
While I am
yes.
at home Abhishek, I'll go for open form 9, then there is this folder. So this will make more sense, like if you are new to this terminal thing.
Okay, now I entered into this PC name. Then I should click run. Run. Okay, now I'm into that run folder. Okay.
Mhm.
Okay. Okay then.
Okay. So
Thank.
all right. So this make this directory. I think it is done.
Yes, done.
Okay, great. Then do the make run and form run. Make directory, sorry, make directory form run. Type this. It will make the run folder for you. Is it done? So please, everyone, till now, copy the case like this case. Copy the cavity case. This is the part to cavity, that is OPT OpenFOAM 9 tutorial incompressible icoform cavity. Copy this to your run folder. I have already copied. Either do it by terminal using cp minus r command, or you can just manually do it like this. Shall we move ahead? Okay.
Sir, where is that cavity is located?
Yeah. So I'm telling you this. So you can see here. Are you able to see computer, like in your open form tutorial, incompressible icoform and then cavity?
Okay, fine.
Sir, where can I find the run folder?
All right. You found run folder, then copy here. Like you can do this paste here direct, or from terminal. This is the command. The important thing is in terminal is you have to use tab. For example, so I am in OpenFOAM 9. So if I do tab tu, I write tu with tab, it will give me tutorial. Then I write incompressible for, then I write in for incompressible, do tab, will show me incompressible. Then icoform, cavity, then cavity, then dot. So use tab, guys. Use tab, and top and bottom arrows in terminal is very important to use. You should make a habit of it. Okay. So now I hope everyone has copied the folder. All right. So now go inside cavity. Go to the folder, or you can do one thing. One second. You are in run, do ls. It will show you cavity. You do cd cavity, and parallelly you can also see this in this background. Inside cavity, okay, you have reached cavity. Hope everyone is inside the cavity folder. Okay. So now here you can see we have, if you do ls, as we did previously, or you can do these. You can use upper arrow to find the ls command. Okay. If you do ls, you find this zero constant and system directory. Okay. So what is zero? In CFD, zero is initial condition, right? So zero are what? Initial conditions. So here are initial conditions for the boundary patches. So here you provide, so this cavity is lid driven cavity problem. Okay. So we are inside cavity folder in our run where we can see zero constant and system directories. So in zero means initial condition or boundary condition. So here you assign inside zero folder the boundary condition for your patches. So lid driven cavity, this is moving wall, fixed wall. And like this is a rectangular domain, and at walls you are giving some boundary condition. And you are defining the initial internal field, that is 0, 0, 0. All right. Similarly, for pressure, you are defining internal field and boundary condition for the various walls, that is top, bottom, left, right walls. Okay, so this is zero folder. Another is constant folder. In constant itself, name suggests the things those are constant. What are constant? Most of the time, our properties are constant. So here it is saying that the viscosity is mu, and viscosity is 0. The fluid viscosity is kinematic viscosity 0.01. Here we define our constant things like, okay, and in system we have block mesh, dict, control dict, these files. These are the files which are used to make mesh, and then while we are solving the equations, what are the schemes and what are the solvers we are going to use? What is the time step? How many how many times do you want to run? How you want to write the data file? Those things are in control dict. Okay, so this is the block mesh dict file. Okay, we'll explain it later. But for now, I want you to catch the feel of OpenFOAM. So for that, we are now in cavity folder. Everyone is cavity folder. Say yes. If no, say no. But
Yes.
don't say anything. Okay. Now we will run one command, that is block mesh. That is BLOCK mesh, MESH. So when we run this command, something happens and we have a mesh. Okay. It is very simple mesh. It is not taking much time. So this is running something. So what it is doing, it is creating mesh from, like it is dividing a domain into number of subdomains from using this block mesh directory. Okay. So you must be wondering, when we are giving this block mesh command, what is happening, from where it is picking the code. So we'll teach it later, like when we give block mesh, from where it is picking the code. For now, you just give block mesh, that is mesh is made. Now you give this command, that is icoform. So this is like solver. So now you have created the domain. Now you want to solve. So for that, you have to give a command for this particular case, that is icoform. Or what you do is you type I. Type I, you do tab. It is showing you all the commands that are with I. Okay, but we don't want that. We write ico. Do tab multiple times and you can see this here. You can type F and then do tab again. It will identify icoform and you have to run it. It is complete, my friends. The simulation is run. It's that simple. Not, it is very simple. OpenFOAM is very simple. People make it hard, but it's simple. I hope you have run this command, that is icoform.
Sir, block mesh, I have a problem with block mesh.
Block mesh command, here it is block mesh. So first, one of the most important thing is that this address should be correct. You should be inside cavity folder. If you are running block mesh inside some another folder, it will throw you some random weird errors. It will not recognize block mesh. You have to make sure you are inside this cavity folder where you have these zero constant and system folder. If 0 constant mesh system folders are not there, it will not recognize block mesh or icofoam. So make sure you are inside the right directory, that is run and cavity. So if you are lost, I'll guide you. So first you have to type run, just type run. Anywhere you are, just type run. It will take you to the run folder. Then you do cd and cavity. You are inside cavity. Inside this, you have to run block mesh command. Use arrows, upper and bottom arrows. You are inside block mesh. All right. Sorry, you have to run block mesh command, and you have to be inside the directory, that is cavity. After block mesh, you have to run icofoam. Ico. I have run it again. No need, but okay. Okay. So you have to write this command, icofoam and block mesh. This is block mesh. So I'll move ahead now. Okay. I hope everyone is done with icofoam. See, saying yes is not important that I have done, but saying no is very important. If you are not saying no, I'll move forward, and it's okay. You can attend the lecture later, but
Sir, actually, in my case, block mesh is not opening. I'm typing it.
so are you inside cavity folder?
Yes, yes.
You are inside cavity folder. So you type OF9. Have you done something anything like that, like OF9 or something like that? Try OF9.
I have typed.
So is it giving you some error, not found, something like that, or it
No,
is
no, no.
working?
It is
Okay, now try block mesh. So in block mesh, BLOCKMESH. So M should be capital.
Yes, yes.
Working now?
Actually, I have small m. I have used.
What is the error actually?
Actually, I have used small m in block mesh.
Acha, you use small m. All right, all right. So use capital M for block mesh. So in OpenFOAM, every second word, like block is one word, mesh is one word. Every second word starts with a capital letter. That is rule in OpenFOAM. You see in open, after open, there is F is capital. So here M is capital. It is running now. Hello.
Yes, sir.
Now type icofoam.
It is running.
Okay, so now everyone type parafoam. Para small, and foam, F of capital, F of foam is capital. And launch it. Something will launch. Type parafoam and enter. It will show you the para view. Just do this apply. It is applied. Now here, okay. Now you are in para view. So you can see here in para you have solid color, U, P, V, U, USA, like cell center and point center, U as cell center, P as cell center. You do U. You can see the initial condition. What? Inlet driven cavity. In this problem, the flow at the top is, so the plate at the top is moving with some velocity, constant velocity U, that is 1. Okay. And at the rest of the walls, the top wall is moving, rest of the wall are stationary. So you can see the velocity here. So for like enter U here or click on U here, and here surface with edges. So when you click on surface with edges, it will show you the mesh. For better view of the mesh, you can see that. So click on the solid color, then you can see it. Okay, so now in this, select view, and you can keep it like this. No worries. This surface with edges. Oh, now you want to see how the simulation goes, to enter it. You can see that. So these are like final simulation. You can see that the velocity has entered inside this. If you want to look at the streamlines, stream tracer, right? Okay, you can see the streamlines as well. So these are very dense. You can see the streamlines. So the point is here the flow is happening like this. Flow is rotating like this. Okay. So everyone has done this. Para view is open for everyone. Okay then. So this is the feel of OpenFOAM, how it is, how things work in OpenFOAM. So what is in OpenFOAM? In OpenFOAM, another for another thing.
Excuse me, Paraform is not open in my is there any
Hello. Yes, I'm not able to clearly listen to you. I hear you.
in my Paraform is not opening. Is there showing fatal error?
Okay. So what your alternative commands are, I'll tell you things. It can sometimes give you some error. Paraform, okay. Underscore
Abhishek,
built in.
yes, some people are using means I think open WSL.
Acha, I don't know about that, yeah. Actually, so what will work there? You have to do touch command.
Yes, touch and dot form time of directory you have to create.
I know. So for the people who are not able to directly access this paraform directly is not working. For those, you have to do this touch. This is a command touch to make any folder. Okay,
Cavity dot form.
I will do that. Yeah. So touch you can give it any name. So you can for now it is cavity case. So we can give cavity name. You have to do this touch cavity dot form. So touch when you do touch command, it will make that like they make that file. So it will make cavity dot form. So I'll show you parallelly here. So when I given this touch cavity dot form, you can see that cavity dot form is file is generated here. Okay, whoever was it, I think it's okay. Now what you have to do is you have to run paraview like this. Are you reached there? Please communicate here.
Yeah, either you can directly open the paraview from the search.
I think Pratyush in this WSL, this paraview command should also work, right?
Yes,
Yes,
it
yes.
should work. If
Okay,
it is
so
not,
paraview,
if it is
you have reached
not
here.
working, then you can directly type into the search bar.
Okay, it's not working then. So you open paraview like this, you don't give paraform command, you write directly paraview. Then you go to files and open this cavity.form like this. Okay, and you can see this running. Is this clear? So the pathway is to use touch cavity.form command, like touch is a command, a cavity form .form is a file name that you generate. Then open paraview, not paraform. You type paraview, it will open, and then you have to load file from here. Okay, so I think this is clear.
See, I'm using an native Ubuntu system and it's again the same problem.
Which problem? Sorry, you are not clearly able to hear you.
I'm not able to open this Paraform or Paraview in this Ubuntu. And to completely
Ubuntu.
yeah,
So
Ubuntu.
you try this. Okay. So it means paraview is not installed correctly, man. Then if you are using Ubuntu, then this paraview command should work. So what you can do is go here and type paraview if some software is coming or not.
Okay.
So you Google it and see if paraview is installed or not.
Or sir, you can do that Paraform dash built-in. At least just let him try that.
Actually, if this paraview is not working, it means paraview is not there on the system.
Yeah.
So it means this paraview, this command is also not working. That means it means you don't have there is some installation problem with OpenFOAM. OpenFOAM should by default install the paraview for it, but I think in your case. So when you type paraview, what is it saying?
1 second. 1 second. Paraview command not found.
So paraview is not installed, or there may be some environmental variables problem that it is not recognizing paraview. So those kind of things. So for now, it's okay, man. Today you don't need to. You have seen it here now. It's fine, I think. You have seen it here. How to do it? Recorded lecture is there. You can practice tomorrow, right? After installation. All right. So we'll move ahead. So I've shown you the basic simulation how it goes. Okay. So you have like one zero folder, initial and boundary condition, constant folder, where you have this folder is generated, which is related to mesh and the properties of the fluid. And third is system folder. Okay, where you have things like how to make things for the like data for how to make mesh, timestamps, finite volume schemes, and every solution. So you have the basic idea how to run simulation. Now you should also have the basic idea of CFD, like how, like what are these for to know like what is meshing or what are these FP schemes folder. So inside cavity, what is this FB schemes folder, what it is doing, what is this FB solution folder, what it is doing. You should have the basic idea of their existence, why they are here. So for that, we'll take 10-20 minutes and teach you to the basic fundamentals of computational fluid dynamics and Navier-Stokes equations. All right. So you must have all studied heat transfer and fluid flow. I'm assuming that. So for Fourier law of heat conduction in a constant fluid means fluid is not moving, it is still fluid. Okay, so there will be only conduction. So for Fourier's law of heat conduction, we know that the heat transfer is directly proportional to the gradient of the temperature from T1 to T2. All right, so K is conductivity. If we consider infinitely small fluid element, then some heat is coming. So some heat is coming from left. All right. Some heat is coming from left and is going toward the right. So that will generate due to the heat gradient or something, let's say heat generation inside a lot of things, there will be a deficit of del Q over del X, delta X. That is simple math. And same in Y direction. Now, if we use the energy conservation law, you'll find this that you use this law that whatever is entering the system and being generated should get out of the system. Okay. So Qx plus dx are entering the system and Qy plus dy and Qx and Qy are entering the system. These are exiting the system. So this is heat generation term and this is transient term. That is if there is a change in the heat capacity of the fluid inside. The temperature is rising, the internal energy of the system will also rise. That is temperature will rise. If we do some math and move ahead, so for transient heat conduction with heat generation, we have got these terms. The first term is transient term. That is showing us the change in storage heat with time or change in the internal energy or temperature. Another term is generator related to conduction. That is diffusion term. So conduction is basically diffusion. And another is source term. And if you do simple mathematics, this is the 2D transient heat conduction problem with heat generation, QB is heat generation, right? Now this is only diffusion. Now what happen if we add advection to it? So when we have only conduction, the gradients are only linear between the plate 1 and plate 2. What when we add, let's say fluid is also moving from plate 1 to 2, that is point 1 to 2, that is u with velocity u. Then we'll also have the heat moving from this point to this point due to the movement of the fluid. So for that we have advection, we have to include advection as well. So okay, so conduction plus advection becomes convection. All right. So conduction plus advection is convection. That is why it is called convection. Now, if we consider infinitely small fluid element in which what is rho u and delta y is the mass transfer. T is the heat capacity, T is the temperature. So it means the fluid is taking heat from left to right. And from taking heat from left to right, there is this gradient that is generated. If we do the same in y direction and we do the heat balance and we are including this here, these equation, that is advection is here, diffusion is this is the transient term. And we do simple math, we get to this equation. Also, if for incompressible flows, we add some things to it and we get for incompressible flow particularly, we come to this equation. Okay, so what this equation is? Transport equation for temperature. So this is basically a general transport equation for any variable phi, be it temperature, be it any turbulence parameter, be it species transport. So for any variable, there is one transient term, okay, temporal term. There is one advection term, all right, where the fluid is taking that variable from one point to another, and there is one diffusion term. And source term can be there always. So this is for any variable phi transport equation. Now, if in terms of, now for this variable phi, if you consider x momentum, then the variable becomes u. And if you consider y momentum, then variables becomes v. And if you replace phi with u, you get the x and y momentum equations in, you get momentum equations in x and y direction. And these are like source terms are like this. The SU is the source term, that is pressure drop, and D is your kinematic viscosity here. So these are the governing equations that most of the people, OpenFOAM solves. That is continuity x momentum and y momentum. It also has energy. So most of and beyond these equations, you can have a lot of turbulence equation models. Like there are one equation turbulence model, two equation, three equations. So apart from these equations, you can also have turbulence equation models, or turbulent equations. So what OpenFOAM is doing is solving these equations. Okay. Now you know that what the OpenFOAM is doing, solving these equations with extra turbulent equations. If turbulence is involved, then otherwise these equations are good enough for laminar flows. Now you know the boundary layer concept. Like flow is this is flow over a stationary flat plate. This boundary layer is developed over time, and in this boundary layer we have gradients. All right, you can see velocity is 0 here, and it is same as u here in this bulk region. So there is gradient. So within the boundary layer, you have to always give a fine mesh. So let's talk about why we need CFD first. Okay, so this is simple flow in a channel problem. So initially, you can see the flow is developing. All right, that is del u by del x and del u by, it is changing with time. Flow is changing with time and in x direction. But for fully developed flow, you can see The flow is not changing with respect to x or with respect to time, you can say. So this is the basic equation if this pipe is circular, r is the radius. So this is perfectly can be done with any analytical solution is present for those. If del p by del s is constant and known, then we can get this profile. And if we consider more complex problems such as 2D heat conduction, in which del y del t, this is the 2D heat conduction problem, then similarity solution or power series solution and separation of variable methods are there in which you can obtain analytical solution for a specific type of shape of the plate or shape of the domain and for specific type of boundary condition. Even then, in those cases, you can't calculate over complex bodies. So if there is more complexities in boundary condition, shape of the domain, or let's say equation, then what we do? We go to numerical methods. So now this is a complete 2D heat transport, 2D transport equation for temperature that I showed you just before. So this equation can't be solved analytically. You have to go for numerical methods. So how do we solve it? What we do is we consider let's say we have a domain the size of this laptop. We divide this domain in a lot of number of parts, and we get what do we get? We get mesh. So this is a one control volume of a mesh, and you can see ij is its location, this red thing, and all others are its neighboring points. This is I plus 1j, this is I minus 1j. What we have to do is we have to approximate all these partial derivatives like discretely. We have to approximate these using discrete method. So for that, the main thing that is used is the math behind it is Taylor series. I will not go into those, but you have to approximate the derivatives. And there you are let's say del t by del x. What you are saying is del t by del x is approximated as the value of temperature at I plus 1j minus value of temperature at ij and the distance delta x, that is this distance. All right, this is how you approximate del t by del x. This is first order. And when you approximate these things, you put in the above equation, you get these equation. All right. So you get this equation. In the what OpenFOAM is doing is basically solving this equation. So what we have done here is we have changed this partial differential equation using discretization methods or approximating into number of linear algebraic equation which we can solve using Gauss-Seidel method, Gauss-Jacobi. There are a lot of methods. Okay, so this is how we do CFD and how we do it. One second. So now what is fundamental of CFD is nothing. First we make mesh, then we do discretization in which we convert PD into system of linear algebraic equations, and we solve this Ax equal to B using iterative or elimination solvers. Okay. So we consider 1D heat equation. This is 1D heat equation. We have temperature, one single plate. We have single plate like this. Temperature at left is T1 and temperature at right is T2. And these are the basic T1 is 100, T2 is 50, alpha is thermal diffusivity, and this is thermostability parameter. If we want to solve this problem using numerical method, then what we do? We consider this plate left at T1, right at T2, and we divide this domain in, let's say, 4 equal parts. Now we have this equation. Now, first we'll approximate del t by del t. Is it time? For that, we say that time at I point, we consider this point as the main point. We said that time at I, at the next time, that is the future time, is n plus 1 minus tin and divided by the time step. This is how we approximate. For second derivative, we do this. Similar to this, we say that gradient del t by del x at I plus 1, that is this, minus del t by del x at I divided by delta x. And if we do the same things here, you can have a look at this in the later. We do the math, we get this equation, and we substitute this and this and this in this equation. We get this. Rearranging, we get this equation. That is time at this main point I. For now, we are calculating at this location. At I is Ti, which is equal to the old time. One second, plus alpha delta T of time at sorry, the temperature at the new time is equal to temperature at the old time plus temperature at the old times at these neighboring points. And this is simple MATLAB code. How it shows, the loop goes like this. For a temperature T equal to, sorry, at a particular time step. So first loop is for time, second loop is for uh, moving over the different meshes. So at a particular point I, okay, it is calculated the new temperature, that is next time step temperature. And this I is iterated over the all mesh sizes, that is I equal to 2 to nx minus 1. So I first it is calculated at this point, then this, then this. So it in a way it is iterating over all the points and calculated the new temperature at the next time step for each and every point. Okay, and it is moving to the next time step, that is the outer loop. So here it is solving for E to the whole plate at each control volume, and then it is moving to the next time step. So this is the basic fundamental. So now what we will do is we'll solve this 1D heat conduction, 1D heat conduction problem in OpenFOAM. So before moving into that, moving into 1D heat conduction OpenFOAM, I want to tell you we have to learn the basics of meshing in OpenFOAM. So you have a one second. How can we hide this, guys? Any puts? Okay. In block mesh, what we have is, in finite volume method. In finite volume method, we have a domain. We divide the domain into very small number of control volumes. So in finite volume method, so OpenFOAM works on finite volume method, not difference. In finite volume method, we have a control volume and we have phases. All right. So let's say heat is coming or some parameter is coming from left going to right. So first we solve in first row, then we move on to other rows. And this is how we iterate over the whole domain to solve it. So OpenFOAM, the phases and control volumes are very important. So OpenFOAM allow us to make complex meshes also, like SnappyX mesh, and interpolation between meshes can also be done which are not equal sizes. And we can also make unstructured mesh in OpenFOAM. Okay, so in OpenFOAM, the important thing is you have a control volume which is called owner cell. So each owner cell has a neighboring cell. Okay, so keep in mind that each owner cell has like phases, 1 phase, 2 phase, 3 phase, 4 phase, and a neighbor cell as well. This is defining neighbor cell is important from CFD perspective and solving a lot of things. So this is what a block mesh in a block mesh looks like. It has a cell center face, owner cell, neighbor cell, and boundary patches. All right. So basically, this is in block mesh also is a hexahedral block, right? Block with, like, this is a cube, something like that, 3D body. So in OpenFOAM, how is this block defined? So this is block is defined like this. So this is first point, that is 0, 0, 0. This is 0th point. This is first point. This is second point. This is third point. And here it is 0th point, first point, second point, third point. All right. And we move in x direction, y direction, and we complete a circle 0, 1, 2, 3. Then from the point where we start in this plane, we'll move to the another plane that is in z direction from the same point. That is 4, 5, 6, 7. This sequence is very important. 0, 1, 2, 3, 4, 5, 6, 7. That defines our block here. You can see here. That defines our block here. this 100, 100, and 100, 101 are number of divisions in X, Y, and Z direction. All right. This is you have to keep in mind this much only. And these are the boundary conditions. So you have to define at the boundary, like you have to define the faces. So you have to, this is moving wall. So here for moving wall you have to define face. And the important thing is in here is that there is a sequence of defining the order of these points should be as per the rules. And what is the rule? Looking from inside the block and starting with any vertex, the face must be traversed in a clockwise direction to define the other vertices. So you have to sit inside the block and you have to see that like a direction of the sequence of the numbers which are defined, and they should look clockwise sitting from inside. For example, 0473. 0473. Let's say I'm sitting here. So how the clockwise should be in another way around actually. Yeah, so 0473 is anti-clockwise sitting from inside. But here anti-clockwise is also working for this case, but the rule says strictly that it should be like this. 0374. Here it is in another direction. Both works in some cases, but in some cases it is better to always follow the rule that is clockwise. So 0321. Or is it 0321? So looking from outside, it is looking clockwise. It is means anti-clockwise from the inside. So here everything is anti-clockwise, but make sure when you do it manually, should be clockwise. So now the lecture is over. We'll go to the OpenFOAM. I
So
hope
can you just
if
tell block mesh once again?
yes,
Last
please.
part is space and
Yeah.
surface.
You want me to repeat?
Yes, sir. Sure.
So yeah, the thing is, so when you define any patch, you have to define the face of the patch. Okay, so here it is defining the face. Patch is nothing but a boundary faces, boundary cells you can say. So when you define a face, there is a rule that the order in which this point should be defined should be followed. So you can't do anything like 3, 6, 3. You can't do anything like the 2, 3, 7, 6 or anything randomly. It should be in an order. What is the order? Or says that looking from the inside the block, when you are sitting inside the block, then the order of these points or these vertices should be in clockwise direction. Okay, but here if you see these can be also in anti-clockwise direction. Anti-clockwise also works in some cases, but in some cases it can throw you an error. So OpenFOAM strict rules are that it should be clockwise sitting from inside. Am I clear?
Yes, sir. Sir, but this is for cavity we can do that, but how for some complex geometries? How can we?
Oh, okay.
identify
So no. So block mesh is capable of making any complex geometry, and that is using these edges. You can for this block you can give any complex arc to this, inside arc, outside arc. So block mesh provide the facility of giving any arc or any kind of complex spline. All right. But for now,
Yes,
it is beginning code, so I'm just saying the simple things. In the next session, maybe in this session, we'll go deeper into those complexities. So
Okay.
let's say if you want a circular arc here, then you can also do that in OpenFOAM. That is possible. All right.
Yes, sir.
Next session will take that. For now, I want to show you. First, you have to learn like how to run basic simulation, and you should have all the ideas. That's why I've given you the ideas of the FB schemes and basic CFD ideas I have given, because OpenFOAM is nothing but basic CFD, right? Like, okay, so we come to that folder again. Please come to that cavity folder again. So now what we will do is we will run 1D heat conduction. We'll solve 1D heat conduction problem in OpenFOAM environment. But before I move into the OpenFOAM environment 1D heat conduction, I want to take a tour of, I want you to take through the tour of OpenFOAM, like how the OpenFOAM is working. So for that, I want you to go inside. So what you do here is you type this command. WM project dir. Type this command, please. That is WM project directory. If you type this command, the terminal will show you OPT OpenFOAM 9 is a directory, right? Hey, someone say yes or no. Is it everyone is able to type this command?
Yes, sir.
Okay. So what you do have to do is press upper arrow. Upper arrow you have pressed. It will show you this command again, and you have to do CD. In front of that, you have to write CD. What it will do is it will take you to your installation folder of OpenFOAM. So wherever the OpenFOAM is installed, it will take you to that directory. Is it taking you to that directory when you enter the command? Please let me know.
Yes.
Okay, great. So now you do ls here. When you do ls here, it is showing you a lot of folders, right? So these are all important OpenFOAM folders, and you need to have an idea what are these folders. So I ran a simple simulation first so that you can have a better idea what are these folders. That will help you understand. So those who are not familiar with terminal, what can they do is go to other locations on the left hand side of this Ubuntu, other locations. Okay. Then you see something like computer, that is your root address. Am I right? Okay. You basically have to go to this folder, OPT OpenFOAM 9. So you go to your OPT. So you go to this OPT OpenFOAM 9. What you are seeing in this terminal is these cases. So these files are nothing but these files that you are seeing in front of you. Everyone is there? Hello? Okay. I hope everyone is there. So first one by one we'll see. So for that we'll just use graphical user interface. What is application? Application is where solvers are there. Solvers like, so what happened when you run block mesh? So you want to know what happens when you run block mesh? What happens is utility, you go to mesh, you go to generation, and you see a block mesh folder here. So when you type block mesh, OpenFOAM is going to the application part, application solver, and it is running this C++ code. Okay, is it clear?
Sir, can you just
So
go a little bit slow?
all right. Okay, so you are in this application OpenFOAM 9 folder.
Yes.
You can also see that in terminal also, right?
Yes, sir.
Okay, so first we'll see about what is the application folder. So application folders are commands when we give at the terminal level. Okay, so in this, let me go to this folder. I'll go to run and then do cavity. So when I'm giving this command like block mesh, okay, it is running something, but from where it is picking? It is everything that you type in terminal is taken from application. So I want to see where this block mesh command or what is the code that it is executing when I run block mesh. For that, you have to go to applications. Application is stands for like apps. In application, these are various solvers. Okay, but for now, where block mesh is, you have to go to utility mesh, and this is where generation and then block mesh. Application utilities mesh generation block mesh. So you can see a make file for or a code of blockmesh.c. Okay, and it is named as block mesh. This is the executable file name block mesh. So when you are running block mesh, OpenFOAM is recognizing this block mesh file. This is this block mesh which I have made here, and it is executing it. Okay. Now another command was icoform. What is happening when we are giving icoform? What is happening is it is going to the application solver. Inside solver, we have various kinds of solver like basic, for combustion, compressive flow, stress for structure is also there something multi-phase. But icoform is incompressible solver. So inside incompressible, we have icoform here, right? So when we are giving icoform command here, OpenFOAM is directly going to this application solver incompressible and to this folder, and it is running this code. Okay. So these are what applications are. It is where every runtime code is there. So the main function. So let me show you one thing. Icoform. So if you have a basic idea of C++, you will know that any C++ code is always executed inside a main function, right? So this is the main function. So whenever you give any command in OpenFOAM, it always run inside this main function, and these main functions are all defined inside the applications. So if you go to this mesh generation block mesh c.file, you can see you'll find a main function here as well. You see main function. Whenever you are running a command in here related to OpenFOAM, it will always have a code which have a main function, right? So this is the main function for block mesh file. Someone please turn off their mic. Is like giving some background there. It is not good for recording. Thank you. Okay. So this application, the next thing is come SRC. Next thing is SRC. What is SRC? It is basically collection of codes which those application files are using. So if you go to any solver, basic. So these are some header files. There are some header files. These header files. So this code is basically telling you to look for these files. Okay. So where are these files are? These files are in SRC. So this SRC is collection of codes. For the code for dynamic mesh is here. Code for multi-phase models is here. And code for mesh is here, and finite volume, like control volume, all these things is here. Function objects for output parameter, this is here. Rigid body motion. So all the code is here which the application uses. Okay. So next is doc. What is doc? So first is it has user guide. If you go to user guide, I have already opened it previously. User guide will take you through tutorials, led-driven cavity flow, whatever, application and lab library. So this is how the equations are written in OpenFOAM. This equation is written like this in OpenFOAM. A bit advanced things, I will not go into those, but this is how OpenFOAM compiles the code. So this is main function, that is application folder. is you can see new app.c. So this is main function. Here you can see the source file, src folder. Here some src inside src folder, some code is written. This is the .c file and this is .h file of that. So what this application folder does is include the definition of various functions from this .h file. All right. It access the definition of various function variables from this .h file. That is, you have to include the header files. And when you have executable of this, and when you run the code, then the linker in the C++ links to the already compiled code of the src file. Okay. This being said, if you have any doubt, you can ask, but you can always go through the lectures and to this file and read it. That will give you more clarity. So the point is, this is in application folder. These things are in src folder, and these header files or make options are used to link the two. This is how OpenFOAM works. Okay, and there is also Doxygen file. You can generate the Doxygen file using /.allw make command. So what is Doxygen is, this is kind of an app. You can also access Doxygen on internet, I think. So if you have any comments regarding Doxygen, you can ask me later. But for now, this Doxygen is important when you are doing advanced coding in OpenFOAM. And these are some tools. Okay. So this is documentation. You should always, you should go and read this for sure. This is very important. I don't know what this is. So there are some things in, these are configuration file, bash rc. So this is for to set the environmental variables, etc. Next is bin. What does the bin hold? Bin hold the application. When you run an application, you get some code that is executable code that is in 0101, something like computer level language. So this bin hold those code. So for example, if I so you can see that simple reactive parcel form is here. This is the code for that. Some solver. So few of the solvers code is here. And apart from that, there you can see form, clean path. These are shortcut commands. So if you do form clean case, it will clean your case. If you do form clean tutorial, it will clean your tutorial. For example, in this case, when you do ls, you can find these post-processing folders that are created, timestamp. If you want to clean this, you do form and cl and you do tab. When you do form cl, there are a lot of commands that are coming to it. You have to do this one. This is the command which is used most frequently. That is form clean tutorial. Because when you want to rerun the case, you want to clean it sometime and clean tutorial. If you run it, you have run, what it is saying, cleaning. It is saying cleaning the case. And I type ls again, what you will see is these files which were generated beyond the basic case are clean. Okay. This form, the code for this form clean tutorial, the code is in application for sure, yes. But you can see the binary file here. Okay. So these contain the binary files. That is 1010. Next is platform. Platform again create the binary file for some of the, for example, some of the solver that we have. Gmesh to OpenFOAM. Gmesh to OpenFOAM means this is the source code. This is the binary file code for when you make mesh in Gmesh and you want to export it to OpenFOAM. And you can also find Fluent to form. There are a lot of things. You can see Fluent 3D mesh to form. If we are making geometry analysis, you can export in OpenFOAM environment using these binary code. So for those also, for these cases, even if I show you, the codes are in application, utility, mesh, conversions. You can see ANSYS to form, CFX to form. So these codes are written in ANSYS. And these use the source code from src file. And then when you give any command, it goes to application. Okay. And these are the most important period that is you're gonna use. Guys, give me a second. I have a sorry for that. Okay. In tutorials, you have so you got when we copied the first tutorial. So from where did we copied it? That is incompressible. Icoform was the solver where it is icoform cavity, and this is the tutorial. So OpenFOAM provides you with tutorial for any of the cases. Like if you want to see a tutorial of multi-phase case, you can go to the multi-phase case, and in that also you can go for any case. Let's say interform, and you can there is the famous dam break case. You copy it to your run folder. Okay, open terminal. You do block mesh. Sorry, you have to. Okay.
Yeah, you need to go to that DAMBreak folder. Yes.
And inside there is another dam break. All right. Inside dam break, you have to run block mesh. Then you have to. The solver name was interform. You are type enter tab, and interform, run it, and I'll show you in Paraview how it looks. You can see the mesh, and you select velocity. You don't want to see the velocity. What do you want to see? The interface. For that, you have to select alpha water. Then it is not showing us anything once again. I think this case is corrupt, but yeah, this case is not okay. But this is how you do. So there is some problem with this case, I think, because at the initial condition it should show the interface, but it is not showing. That's okay. Like it has some problem. That's okay. But the point is that whenever you want to run your own simulation, you have to copy a case from tutorial. Copy a case from tutorial. See which is the best case where you'll find whether you are using combustion or compression flows or discrete element methods. Direct numerical simulation for turbines is also the electromagnetism. Financial, you can also do heat transfer, incompressible, Lagrangian approaches. Mesh, you also have solvers like test cases for the mesh. You want to test some dynamic mesh capability, you go for the test, you go looking for the test case here, like move dynamic mesh, refine mesh, snappy hex mesh, multi-phase resource access analysis. So basically, you first have to go through these cases. And what are WMake? So when you are using, so let's say you have made your own library. So first of all, when you are compiling your OpenFOAM, all the instructions for compilation are in there only. In this case, in this folder. So these are like instructions for the make files. How do we make? What are the instructions for platforms? SRC folder instruction. Okay. So for example, if you open any of the files, we will not open any file. It's just that whenever you make your own library or whenever OpenFOAM compile anything, it go looking for the rules of compilation here. Now we'll move on to our case, that is 1D heat conduction in OpenFOAM, and we'll do that. So guys, here we'll take a 5 minutes break. I need to drink some water, and we'll be back exactly at 7, like around 7:40. Before 7:40, around 7:40 we'll be back. maybe before that, but 7:40 is the last. Please, everyone, be back by 7:40. We are taking a break. Meanwhile, if you have any doubts, you can ask. I think Vipul is there. Hello, Vipul. I think he left. So please take break. We'll be back by 7:40. Hello. I hope everyone is back. Am I audible?
Yes, sir.
Okay. Thank you, Kapil. So we'll start. Now, what was the next thing was you wanted to simulate 1D heat conduction. Okay, these are what the parameter. Parameter you can take anything. That is, so this is the hands-on. This has more hands-on part. So first of all, you have to go to your run folder. Okay, let me clear the screen. You can clear the screen using this command. Everyone is there. Hello, I'm audible, right? We are starting again. You can use this clear command to clear the screen. Now what you do is simply type run. You type nothing. Type run. You have typed run. It will take directly you to this run folder. Hello. Now what you have to do is you have to copy any case in which, so now what we want to do is we want to simulate this 1D transit heat conduction. That is the simplest form of thing that we can solve in any CFD software. Now we want to solve 1D heat transit heat conduction. Now you know that temperature is what? Is not a vector quantity. It is a scalar quantity. Okay. So now what we will do is first we have to find the solver which only solves scalar quantities. Okay. So first for that, that is the solver. There are solvers, there are then their basics, the Laplacian form solver, potential form, and this is scalar transform form. Okay, guys. So this scalar transform form is for any scalar, right? So we will try to copy and paste a case which has this, which works on this scalar transport form. Okay, that's it, the first thing. You find, for example, if your problem is multi-phase, then you have to copy a case which is more parallel, more similar to multi-phase. Now what you do is we'll copy a case. We will do OPT. We have to go to OpenFOAM, tutorials. In tutorials, basic. And if you do double tap, it will show you. If you do tap 2 times, it will show you what is inside this basic. So here we are trying to copy a solver to study the heat conduction, and that solver tutorial to study the heat conduction, and the solver that we're gonna use is scalar transport form. So we have to go to your OpenFOAM folder tutorials inside basic, and we have to select a tutorial case which is inside the scalar transport form. You have to go into tutorials. If you do double tap, once again, there is only one case in scalar transport form. In this, there is only one case, that is Prince Daly case. Okay, so we can change the name to like what heat. We want its name to be changed, and we want it to be present in our run folder as the name heat. So we'll go to the run. Okay, I am entering this command. You can see there is heat folder here. Please do this much. CP minus R means copy the directory. Go to OpenFOAM tutorials, basic scalar transport form, and paste daily case. Copy it and rename it and it has heat. This heat rename it. I think this much is clear. Now what we'll go to CD heat. And if you do ls, you can see 0 constant system folders here. Order is also there. It is like commands which are already there. In order, you can see this is plus the block mesh. It is running block mesh, and then it is running applications. It's not of, we'll not discuss this much. So first and foremost thing we have to do is run block mesh. Second, cannot find file. Block mesh is not there. Where is it then? Okay. So here you see you don't have any block mesh file. So what to do? What you do have to do is copy block mesh file for. So you go to the scalar basic tutorials. So you go to OpenFOAM 9, you go to tutorials, and you go to where, take any basic, let's say application form, try to see mesh here. It is not. Block mesh is not in basic cases, guys. So we have to copy the mesh from somewhere else. Okay. That's how it is in OpenFOAM. We will go to ICO form, cavity, okay, system. Anyway, you can go to anyone, but we have to go to tutorials, incompressible, ICO form, cavity, and system. There you can see block mesh file. Because the folder that we copied, it doesn't have an block mesh file. And copy this on in our heap. Block mesh is there now. This much is clear. Should I move forward?
Can you please just show the earlier commands actually to follow that it takes time. So can you just show
Okay. No, yeah. So what I did is, so all of you are able to make this heat folder, right?
that just a little bit earlier one so that at least we can create here. We'll keep
Yeah,
the
this
screen like
happened
that so
because,
that we can follow the same
yeah,
commands actually.
okay. This happens actually, ideally, if you are online workshop, you should have two PCs, two laptops. That works faster. If you are not able to do this through command line, hello, if it is taking you
Yes.
too much time, you are open to, sorry, you are new to this environment,
Okay.
then what you should do is, if you have a look
Okay.
at here, you should go to tutorial,
Okay.
incompressible. You are using WSL,
No, virtual VM.
so you go to incompressible.
Okay.
Inside not in, do you go to tutorial, you go to basic, all right,
Okay.
and you go to scalar transport form because temperature is scalar quantity, and we are
Okay.
studying only conduction. You copy this Pitts daily case, all right. You come
Okay.
back to your run folder. Okay, it is already pasted here. I deleted this, and you paste it here like this only,
Okay. Yeah,
right?
okay. Okay.
So that is initially I know this will be a problem, and you rename it as heat. Manually you
Okay.
can do it from here.
Okay.
That approach is easier to see. That I agree.
Okay. Then. Okay. Got it.
Initially you should do the like that only. With time you will get the hang of this terminal bash terminal commands.
Okay.
Okay, yeah, okay. So one thing you can also do this. Just listen to me first. That you go to
Yes.
heat, you do right
Okay.
click. It will
Okay.
automatically open the heat folder.
Oh,
it will open the address of the heat folder. Got it?
okay.
So that will be better that way for you.
Okay. Okay. Thank you.
Now you are in heat folder. So do that and let me know. So this is the path tutorial basic scalar transport form.
Yes, I am in that heat folder right now.
Heat folder. Cool. Now do one thing. Open in terminal.
Okay. Okay. That I did.
Now run block mesh.
Okay.
What is it saying?
It ran. Run completed.
It ran like this.
Yes.
Oh, in my case, block mesh file was missing. Okay, no problem. Great. If it is running, that's fine. I hope everyone is here. Now the next part is that we have to change our. You can see this is a 1D mesh. This is a 1D mesh, 1D heat conduction. So if you open your block mesh file and open it in Genie so that you guys can see. Okay. So if you see your block mesh file, first is convert to meters. Okay. Keep this as 1. Like if it is 1, these points are in meters. If it is 0.1, then centimeters, like that only. Right? And these are the points. Open your block mesh dict file, please, everyone. This is your 0th point. This is your first point. This is your second point. This is your third point. This is your fourth point. This is your fifth point. Sixth point. This is your seventh point. Okay. Now I showed you previously that this is how the block mesh looks like this. You have points like 0, 1, 2, 3. So 0, 1 is x direction. 1, 2 is, so actually you don't have to do this one. It is only just for you to show you that these are the point numbered as this. So if you have looked at the block mesh dict file, you must have seen that at 0 to 1, 0 to 1, first two digits are in x direction. Second two vertices are in y direction. That is 1, 2. That is 1, 2. And the another vertices, that is 2, 3. 2, 3 is again another direction. Then 1, 0, 0, 1. Okay, so 0, 1 in x direction, 1, 2 in y direction, and this 0, 4 in z direction. So first point in x direction, another point is, and this is number of division in 0, 1 and number of division in 2, 3. Like sorry, 1, 2. X and y direction. The first thing we have to do is we have to make it is 1D. So we'll give 50 points in x direction at 0 points in 1 in y direction. Okay. This is also, you should also change this to 0 0.1. So in y direction it looks like 1D. So both y and z direction have smaller length. Okay. So we have make a mesh which is 1D in domain. So we'll just try to build it. One second. Okay. It is running, no problem. So if you open Paraform, so we'll go into details of block mesh later, but for now, okay. So it is give us an error that what it is saying is home Abhishek OpenFOAM machine are run that T boundary field, one of the boundary field is not there. Cannot find patch moving wall. This is the error. So now we have created the blocks. Blocks is ready, but the boundary. So the boundary wall we also have to change. So what we will do is we'll give the left wall as left, right wall as right, top and bottom and side walls as top, like other walls. Okay. What we will do is we'll first give left wall. Okay. We'll go left wall. So left wall point is looking from inside clockwise direction 0374. 0374. Okay. Looking from inside 0. Yeah, it is clockwise. 0374. Okay. Let me try if it is correct. Block no. No, it is not correct. 1 second. Zero. Okay, so this is the correct actually. 2, 3. You can check. Okay. 1 second. Okay. So before doing that, what the error was is error was left. So it is saying that we can't define two faces at different boundary path. So first I have to copy this. This is our left 0374. Okay. So 0374. All right. It's fine now. Play running now. So these are left wall. What is right wall? Right wall is it's looking from inside clockwise. Should be in the, it should be like 1562. Yeah, 1562. So you'll find the right wall is 1562. It is okay if even like this is okay. Any questions, please, you can ask also. I'm not seeing your comment. Okay. All other walls are of no use to us. So we'll put everything else in walls. So you only have to give left and right boundary. All right. You only have to give left and right boundary. Rest, just put each and every face in other. So please update these boundary condition. Please, these are on your these are on my screen. Please update these boundary conditions. Check it. Okay. Please update these boundary condition in your folder.
Can you just tell how you open the block mesh dict? Just
Okay. Yeah. Please ask these questions. Please. Don't skip on this. So you have to go to system and then block mesh dict.
Okay.
Yeah.
Could you please open the block mesh?
Yes.
Action.
I am. Keep everything as wall and other is empty because we are only doing 1D simulation. So we are moving from left to right. There is no other walls. Sorry, there is no other grid size in other direction. So keep everything other as empty. Is it done? Actually, you don't have to write one by one, just copy and paste. Like the previous block mesh dict file, you have to copy paste the vertices, like the faces only. You don't need to delete everything and write from scratch by looking at the screen. Are you guys done? If no, please say no. Okay, I'll move forward. Now, what you will do is run the block mesh command again. All right. These points are also here, so you can have a look. Now, what you have to do is block mesh command, run block mesh command again. It will change. You can see that your bounding box is from 0 to 1 in X direction, 0.1 in Y direction, Z direction. And these are number of points, cells, and faces, internal faces, everyone you can see here. Okay. So where does it get stored? It gets stored inside block mesh. One second. Let me show you also. So foam. Meanwhile, other people can copy these left, right, and other boundaries. If I do foam cleaning tutorials, right, then do ls. Then inside constant, if I do ls, you can see there is only transport properties. There is no mesh file. Okay. But if I run block mesh again, I'll run not type block mesh, I'll just use upper arrows, block mesh. If I run block mesh, it says constant. Okay, sorry. I was inside constant folder. We have to run everything inside sheet folder, that is main folder. So if I run block mesh again, now if I show you ls constant, so if I show you the constant folder, you see one more file is generated, that is block mesh, polymesh. This polymesh file contains contains faces, neighbors, owners, points. The points are the like the vertices of the block mesh, and other points, other mesh points. Owners are the owners cell, neighbors are the neighbor cell, faces are the faces, and boundary is the boundary. So I'll open the, what we will do is next is we'll go to the boundary folder. So what I want you to is go to the boundary folder. Boundary, there is file generated inside constant, polymesh, and boundary. Open that. This is the file. You can see the here inside constant after block mesh there is file generated. that is polymesh. Inside polymesh, you have to open the boundary. Are you guys there? If you are lagging behind, just let me know. I'll stop.
Yes, sir.
You are there, great, great. Anyone else? Please say no if you are not. So if you can see that inside polymesh we have owner, neighbor. These are the various points. How many owner cell we had? 251. Okay. How many points do we have? 204. How many faces do we have of the mesh? 251. But boundary is special because boundary tells us what are the various boundary. One is boundary left, like wall, number of faces 1, and start face 49. Similarly, the other faces. But now, if you want to see our mesh, like how our mesh looks, what we wanted to do, we want to we will want to do paraform, na? We want to look at the mesh in paraview. Now, if I run paraform, okay, it is throwing us some error. What it is saying is cannot find patch field entry for left, and where it is not finding this thing, it is not finding inside run heat 0t. We have, so there is a boundary file which is generated here, but we have not updated our boundary inside 0 folder. That is a boundary condition. We will open both in GNU. Okay, so this is our temperature file. What we will do is, so here you can see inlet, outlet, upper wall, lower wall. So it is not like that. Boundary conditions are not different. What are boundary conditions? Left, right, and other. You will have to change this to left. And just hit those. To change this one to left, and at left we have a temperature. How much? Let's say we have a temperature of 1. Will not change this. We'll keep it as it is. Now on the boundary, we have a temperature of. We are giving at right boundary temperature 0. Okay. At right boundary, we are giving temperature 0. Internal field initially is 0. Everything is 0 initially. And this will do other. Okay. I hope this is understood. What you need to do is you need to change those boundary conditions. So please change your boundary condition to this. Similarly, we'll change the boundary condition for u, that is velocity vector. If you are done, let me know you are done. Then I'll move forward. Okay. So now we'll move on to velocity boundary condition. If you're getting something like this, don't worry, just delete it. From non-uniform, from list, delete it. And because this is a velocity vector, you have to do this like this. Inform 0, 0, 0. Semicolon is also there. So instead of, so we need to apply this 0 gradient velocity condition. Okay. So what we will do is we copy these boundary condition. So for velocity finish, we'll also test velocity, no worries. Okay. Initially, we are not giving any velocity. Velocity is 0. This is the velocity field, boundary field. Make sure you give these boundary condition in the velocity field. Nothing, you just had copy paste these, and instead of this uniform 1, you have to give a bracket of 0, 0, 0. I think everyone is done till now. We'll give you 5 minutes to do this. Let me see. ML session will be next week. So I'll move forward. You are done with this, please. Anyone reply if you are left behind or something. Otherwise, I'll move forward.
Can you wait just 2 minutes?
Yeah. Please, Kapil. If you are doing it, don't wait. Okay. So I'll keep these open while move forward with things. Okay. So now this error should not come because previously it was saying that cannot find patch field entry for left inside the 0 folder. So now we have gone into the 0 folder and we have like changed the boundary condition for T and U. It should not give us the error, any error. So we'll go into like directly into paraform. Kapil, are you done?
Yes, sir.
Hello. Okay, great. So if you go into para, you can see this is a one-dimensional mesh. Okay, this is one-dimensional mesh. And you can also look at the patches. If you go here, you click on all the mesh parts and unclick them, and you go to the right. This is right wall. This is left wall, and this is others. Others are all walls. Okay, you can always check your mesh like this. All right. Now what we will do is we will run directly as one. Next thing is we have to go to constant folder and see the properties. This is what this is diffusivity. We have to like this is 0.01. I think this should be fine. It should not give us any issue. Okay. So let's keep this as it is 0.01. Okay. Next we will go to system folder. We have seen block mesh. We'll see each and every other folder. What are they saying? So first we look at the control dict. It is saying application is scalar transport form. So this is the code that will run. That is scalar transport form. We will start the simulation from start time, and start time is 0. You can always also keep this as latest time. If you want to run it from the latest time, you can always do this. That is latest time. So for now, we'll start from the start. Stop at end time. And what is end time? 0.1. What is the time step? 0.001. So it means it will run for 100 time steps. Okay. Not 100, sorry, 1000 time steps. Write control is time step. That is, it will write after few time steps. And how many time steps? 50. After each 50 time step, it will write a file. Okay. Which we can see in ParaView. And write control IST, and these are all light precision, time, format, general precision. And there is something purge control 0 means I think I forgot about this, but you can always Google it or something, ask ChatGPT. Like for now, it is no user for us. But these are the things you should know. Okay. These are like how like time step and all those things. Now FB schemes. So what are these? So when I told you that we do finite volume discretization, when I told you those things, now like here, not here, here. This is what these are how the discretization is done. So this is the simplest form of discretization. These, but there are more complex, more harder, specific to many problems. Discretization are there. All right. So what are the those discretization schemes that we want? So for example, from time, this is Euler. From gradient to calculate gradient, this is one scheme. For divergence, this is scheme. So these are various schemes. And how to solve the A matrix. So we have AX equal to B matrix. Okay. So for that, how do we solve it? What kind of solver we want to use? So what kind of we want to use is this. Is something P by conjugate stabilized gradient method. So this is its name. So this is the solver it is using. The tolerance is this. So these are all CFD parameters. Okay. So these are, so that's why I've explained you the basic of CFD. That is, you should know why the FB solution file is there. To select the solver type. Why FB scheme? To select the which kind of discretization schemes we are using. Okay. And control dict is your control dict file. So you don't have to change any of the change to these things. You'll just run the scalar transport form. So for those still stuck at U and V, I am just opening the U boundary field for you. You can have a look from here. On the parallelly, we'll run scalar. If you do SCA, scalar transform will come. And then do tab. Simulation is done. Okay. Everyone has done scalar transport form application. Please say yes. If yes, now what we will do is we have run the simulation. We'll see it in Paraview. If anyone wants me to stop or show any previous file, let me know. Okay, we'll open Paraview and we will see our result. We apply, we'll see initial condition. Initial condition is t equal to 0 and we'll run it. So right now it has not reached steady state. So we can plot the velocity profile like this. Plot over line, x direction, like this. You see, right now in this time step, in this much of time step, the temperature has only reached till this point. And at steady state, it will be like, yes, at steady state, it will be a constant gradient. So for to do that, what we can do is we can go to a control dip file, change the end time to let's say 10, and increase the time step bit. Okay, those things we can also do. Always. So 10 and 0.0, we have to increase the time step, guys. And I'll open another folder. So what I'll do is I'll run the scalar transform form again. It took a bit longer. Now I'll again, what you have to do is you have to do these changes. You have to do these changes and then run the simulation again. Because in this less time, the temperature from left to right could not reach a steady state. It was still in transient. We want to see a first order profile, that is the linear profile of temperature from left to right. Now let's see Paraview again. We'll go to temperature. You see velocity is 0 because we have not given any velocity. Now we are only given temperature. You can see temperature is steadily moving forward. I think in this much of time it should reach a steady state. Or we'll directly go to the final point. This is the final point, and we'll see the profile now. So it has almost reached that is simple line, that is straight line. If we increase the time step, decrease the time step bit, increase the total time, it will reach a steady state. Okay, we can always practice those things. Now, next thing is what we will do is we'll go to u velocity and we will change the internal field velocity at left, and what we will do is we'll change the velocity here as 1, and here we will do this. There are many ways to do it. We want a constant velocity of 1 in x direction. Okay. What we are giving is a boundary condition like this. So we gave a velocity of 1, 0, 0 like this. Okay. Also, let me show you the profile, state profile also as well. Okay. Oh, sorry. We have changed the U as well. No, that it. Okay. We can see it has almost come. It takes time for simulation, but you can see it is almost parallel. Okay. So now what we if we give velocity, so it is like similar to state. We have like compromise the time step a bit so that it runs fast. It don't take much time, but you can see it time step is very small. It should be small, should not that be that large. So we have compromised the time step little bit, but it has given us almost state profile. If you go for more time, it is running for 20 seconds. If we run it for more seconds, finally it will give us a steady state. All right. Okay, this much is done. Like if you give velocity here, let me do this. Now, if you go to U and if you give velocity here, the profile will change for sure. Let's give me a point 0.1 velocity in X direction and run the simulation again. You can always practice those things at home and just showing you. Now you can see the when we give some velocity, the profile is completely changed. I'm removing the profile is completely changed. Previously, it was like this. It was almost straight, reaching steady state. Now we have given velocity in this direction. Due to the velocity, there is there is heat flowing from left to right at larger rate, and due to that, the steady state profile looks like this due to the velocity introduction to it. So this is it. Okay. If you have any question about this case, please let me know. Any question about this particular case, please let me know. You can practice anytime later, but if you have any questions regarding this case, because now we'll move to another case. We'll run one more simulation. Anyone? Okay. If not, then we will move forward. So we'll delete all this case. Now, next thing we have to do is in the same run folder, we'll take a icoform case, that is cavity case, and convert that case to flow in a channel. Okay. So what we will do is similar to previous version. And now I'm not going through terminal because a lot of you guys might have problem with it. So I'll go with GUI, that is using the normal folder thing. OpenFOAM 9. Okay, I go to tutorial. Then from tutorial, I have to take an incompressible case of icoform, that is cavity case. I'll go for here. Inside incompressible, the cavity case is in icoform. Inside cavity, again, one more cavity. And I copied this cavity case. So I copied this cavity case from this address, and I have already this case here. I will delete it, and I will do paste here. I have this cavity case here. Now what we will do is, if you quickly go, you do block mesh, and icoform, if you run icoform and do paraform, apply it here. Look at the velocity, u velocity vector. Then if you look at this, you can see the the boundary conditions are not as we want. So top one is moving wall, content fixed walls are another walls, and these are the various walls. Top and other walls, and front and back are front and back. The point is the mesh, the boundary patches and the mesh is not what we want for our kids. Okay, so we have to first change the mesh, then we have to change the boundary conditions, patches, and then we have to run the simulation again using the same solver. We did not change the solver. Solver is same. That is icoform. Okay. So what we do is form clean tutorial or form tab CLE tab clean tutorials. We'll clear the screen. Now what we will do, same as before, we'll open our block mesh script file. And you know that this is our 0.1, third, fourth, fifth, sixth, seventh. Okay. So now if we look into flow in a channel, uh, then we can consider a like we can consider any problem. Let's say we want flow in a channel with length in x direction as 5. So our x direction length is 5. And because this will be a 2D simulation, we want our y direction to be let's say 0.2. Okay, so we want a very, okay, let's keep it simple, 1 and 10. One, 7, 1, 7. Okay, to do it 10, we are basically what we are doing is we're changing the x vertices to 10. So this means length of our pipe is 10. Okay, and y vertices we are keeping as 1. It means y direction is 1 and x direction is 10. Now in x direction, let's divide in 100 domain, and in y direction let's divide in okay, so let's keep it in 20 domain, because in y direction we'll have boundary layer. So as I told here, in this case, particular case, this case, this boundary layer needs to be resolved because most of the gradients are in this boundary layer. Here we don't have gradient, it's just flat. It's just bulk region, the velocity is not changing. The velocity is changing in this region. So we are giving a bit larger number of spacing in y direction. Okay. This is done. Now what we have to change is, now what we will do is we'll do this left boundary. Flow is coming, flow is coming through inlet, flow is going through outlet. So we'll keep this inlet, this outlet, top and bottom will keep as top and bottom, and others are front and backs are empty. So inlet is 0473 and outlet is 1562. So we change this to inlet, and this will in type we'll do it like patch. This is not a wall anymore. And patch is whatever the patch his name is 0473. Okay. Okay, the same thing we will do for outlet. We will do this copy and paste. Change this to outlet. and you see the right wall is 1562. You will find the face with 1562, which is this, and we will paste it here. Now the important thing is top and bottom. Top and bottoms, the type is wall. Type is wall. So what are the top and bottoms? 3267 and 0154. These are the two. Okay. Okay. And front and backs are empty as usual. So these boundary condition you have to, these boundary condition you need to give. Front and back you have to keep same. These you have to change. Okay, guys. Now what I will do is parallel. You can see I'll check if this mesh is okay. We are inside cavity, all right. And what we'll do is block mesh. Okay, so you can see now the inlet, outlet, top and bottom, and front and back are made. All right. So what we have done is we have changed the boundary condition as usual in the previous case. We are simulating Hagen positive flow. We are making that kind of geometry now. If you have any doubt, if you are copying and want me to stop, please stop me. Let me know. Okay, I'll move ahead. All right.
Can
So,
you please scroll down the front and back?
what please? Sorry.
The front and back patch name.
Acha, front and back. Front and back are the same. Front and back are the same. No change in them. The point is, it is previously in the cavity, the front and back remain the same. Na? So we have in previous version, we have top wall, moving wall, and bottom and left right walls. Those were stationary walls. Front and back is the same. So what we have done is we have changed this region to inlet, outlet, and top and bottom. Got it?
Yes, thank you.
Okay, okay. Great, great. These are done. Try running your block mesh. It should run. It should show you this. Is it showing you that?
Yes.
Okay, good. Now we'll move ahead. What is next part? You know that this mesh is okay, but whenever we will try to run ParaView, Paraform, it will give us an error. That is, it will exit automatically. That please also do changes to your boundary condition. Same procedure will follow as previous. You should always, what you should do is you should go to constant folder, then polymesh, and then open your boundary file. Okay. So this is your boundary file. Like just to have a look at it, like the boundaries are perfectly defined. You have four boundary patches. Now you go to zero folder. Okay. Copy both, open both pressure and U velocity field. All right. So here you had like moving wall, fixed wall, front and back. Front and back will keep as it is. But for pressure, moving wall and fixed wall, we have to change. Okay. So what we will do, we will first change the moving wall to inlet. So when we look at the Hagen-Poiseuille flow, you can ask ChatGPT, or you can we can ask ChatGPT right now. He's open. He's always there. So he will give us the basic parameter to simulate Hagen-Poiseuille flow. So he's saying channel height should be this, channel length should be this, that's okay. Width should be this, kinematic property, density. Inlet, so at inlet we have fixed value. Outlet we have to give zero pressure. And walls are no slip. That is fixed value. So, but what about pressure at inlet? Pressure at inlet is zero. Okay, zero gradient, not zero. That is Neumann boundary condition. At right hand side type, we have to give fixed value, and inside the fixed value we have to give as zero. So at the right hand side, we have to give pressure as zero. You can see here, pressure value zero. Zero pressure for outlet for the reference. All right. Next boundary conditions are, next boundary condition will keep as no slip, zero gradient for pressure. Copy this and we'll, what are the boundary conditions for the top and bottom walls? These are walls, so we'll, zero gradient boundary condition is there for pressure. I think, then make sure the names are correct, top and bottom, top and bottom. Yeah, it's correct. Top and bottom, okay. So these are boundary field for pressure. Similarly, we'll change the boundary condition for you. Everyone has done this. Now what we will do is we'll copy these things directly paste into the u velocity profile. Sorry, uh, u velocity boundary condition. But at inlet we have to use this kind of boundary condition. That is, at inlet we have to define a fixed value, and fixed value we are giving is 100. Okay, and but right boundary we have zero gradient velocity boundary condition, and top and bottom is also I think we should give no slip. Okay, sorry. You can look for the pressure from here, pressure boundary condition here, and u from here. So for pressure, for Hagen-Poiseuille flow or flow in a pipe, 2D pipe, flow in a channel. For pressure at inlet we have zero gradient, and at the right that is outlet. Okay, nobody is correcting me here. So we have to define it as outlet, not as right. So at outlet we have to give a reference value. That's we are giving it. That's why we are giving a pressure of zero. Top and bottom are zero gradient for pressure. But for velocity boundary condition, at inlet we have to give inlet velocity, that is one. At outlet we are giving zero gradient velocity, and top and bottom is no slip. Okay. Now the next thing we have to do is Go to the transport properties. So mu is 0.1. So, so what ChatGPT is saying is property kinematic viscosity should be very less. Okay. Let's give two or more like 0 point approximate value like this. Now we'll have to go to the time step. These things will not disturb. These are okay for now. For the basic, we will need to change the control dip. Delta T end time is 0.5. You change it to 50. And right after every 50 times. Okay. Now what we will do is we run the simulation. First we run block mesh. Then we will write the solver name. What is the solver name? Solver name is always written in the control dip file. You can directly copy and paste it. So keyword expected keyword uniform or non-uniform found on line 30 of P boundary field outlet. P boundary field outlet. Okay, reload the line. A second. So in the P boundary field is uniform 0. Okay, value we are not stored value. It should be uniform. These kind of errors may occur. That is saying one more error expected keyword from. Now the same thing it is saying us in U. That is uniform is missing. Okay. These things you have to see. Now it is running. Let's take minutes, few minutes. May take a minute. How many times that we did give? Actually, these values are not standard values for you transport property. I'm just taking random values. It's just to show you that how to run simulation. You can always go to ChatGPT and take a standard case, but that might take a larger time to run. Okay, it's complete now. Now, first, let's check our boundary conditions are correct or not. For that, you would remove first everything. Now, where is your inlet? Here, here is your inlet. Okay. Sorry. Here is your inlet. Now, where is your outlet? Here is your inlet and out. You can see that inlet, outlet, and top and bottom. Yes, the boundary conditions are correct. Let's just do that to see how the simulation is going. No, that's not it. I think viscosity is very large. You can see that initially it is not fully developed here. Profile, it is different. Here it is like kind of more fully developed profile. All right. Let's go to the last time step. Okay. So now you can see that the profile is slowly developing over these regions. Now what we have to do is we have to plot our line to see whether that parabolic profile is coming or not. Okay, so for that what we have to do is we have to plot our line Before plotting over line, just have a basic idea of the length of the domain. For that, you can go to this state axis grid. Okay. Okay, so that's fine. So now we'll plot over line at 3 point, let's say here, here, and here. I think we can't plot on multiple lines. Let's see. First, we'll plot at the center. That is in y direction, but at the center. So we are plotting at 5 point, like the center of this channel and in y direction. You see the velocity is like this. So initially we have, so this is I think not fully developed profile at this point because it is getting developed. We have given uniform velocity profile. The profile is developing. So here it is not developed. You can see the bulk region. Now if we change the x to the 10, okay, you see a more better profile than the previous one. Okay, all right. This is so if you increase the length and increase the time, it will. So you can also do one thing. This you keep this as 10. Okay, like we are plotting at the outlet here, so it is the outlet. Just little of bit behind outlet is okay. All right, now it is better. So what we will do is we'll go to the first time step. You can see at first time step velocity is 0, and we are running the simulation with time. You can see the profile is getting established with time because initially it takes time and some length from the inlet to fully develop the flow inside it. Even we need a little bit more length to get it fully developed. That is again, you can juggle with the parameters of kinematic viscosity or the thickness to width to length ratio of this channel. Those things you can do. Okay. Now, if you have any questions regarding this, please let me know.
Hello. Actually,
Hello,
one
yes,
doubt I'm having regarding that plot over line, how you made that?
yes. So it's simple that you have to go to this plot over line. There are various. So these are to plot contours, clipping, slice. So these are for these first three are for beautiful plotting like 2D, 3D plotting of contours and slicing planes, and these are for vector plot. This clip is for vector plot. This is for streamline, and this is wrap by vector. I'm not used much. And after that, these all for are all line plots. This is line plot over time. Initially, we have like flow field plotting, then streamlinings, and then we have plot over lines. So here, this is one plot over line. So you have to select that plot over line, and then from here you wanted to plot in y direction, right? You have to click y direction. It will automatically give you the center point. But I want to plot in, let's say, the rightmost point, 9.5. Okay, then I just click apply, and it will plot me. It will plot me variables. So you can go to the bottom as well. You can plot a lot of things. If you don't want to see pressure here, you can also look pressure. So let's try that. Yeah. So you have seen velocity here. You want to see the pressure, how the pressure rises in the center line from inlet to outlet. So for that, we'll choose x-axis from 0 to 10. And here we are choosing center line. Okay. 0.5, we are choosing center line. Now we'll do apply here. You see velocity is like this, but we don't want velocity here. We want to see pressure. You see the pressure is like this. So pressure, we are getting a pressure drop of around 0.30. That may be, I think, in Pascal or something. And here at outlet, we have given the pressure 0 because we wanted a reference value for the pressure. So at outlet, you can see the value is 0 and it is rising like this. So actually, it should rise linearly. Del P by del X is considered a constant, right? But because we have a non-fully developed flow at inlet, it is giving us some different curvature. This has not reached a steady state, so that's why it's looking like this. Ideally, in a fully developed flow, it should be like a straight line. I think that is clear, sir.
Yeah, it's clear now.
Hello.
Thank you.
Okay. Hello.
I have a
Yes,
small
sir.
doubt actually. This point one, point two you're telling, like, can you just physically show where, like where and where in the plot? Actually, it is just like
Plot is
just for like
yeah.
in which.
Okay. 1 second. Let me just go there, and I have to turn those off. The point one is just like it is at the center point. You can always look those things. Yeah, no problem. But I'll show you anyway. So this is our domain, right?
Okay.
So when we are doing this plotting over a line, let's say in y direction we want to plot. So these points you can see here. It is showing here. It is like behind it.
Okay.
Yeah.
Yes.
We can also adjust the line from here, but it's always better to write points here. So what we'll do, directly click this y. It will by default assume the center line. If you want to plot at let's say uh, at this point, that is let's say 2, then we can do 2 and 2, and if you do enter, it will move to here. You can
Okay.
increase this length, it will show like this. But R is from 0 to 1, so it is showing like this.
Okay.
You have to do enter. So this is here, you can see line here. Those
Okay.
things you can do, yes.
Okay.
If you do apply here, you can see a line. So for pressure, I clicked off, I just wanted to see U magnitude. And you have to click here and here like this. You click on left, you operating in this zone. If you want on right screen, you are on this window. So if you want to see the evolution at this point with time, then first you go to 0 time. This is 0 time. Now you see the velocity 0 at this point, midpoint, wherever we were showing things. This point, okay. All right.
Yeah.
This point. At this point, evolution with time is like this. You see, it is getting stabilized. You can see it like that. So if you want to see in this, the animation, you have to click on this. You want to see in this, you have to click on this.
Okay.
Yeah. So these are just the basics of OpenFOAM. If you have learned this much in 3 hours, that is, I think, is very big achievement. Because when we used to learn, like it was not like that. Learning from internet was very nowadays ChatGPT is there, so it is easier. But learning from internet OpenFOAM is difficult. I think this is clear for now. If you have any other questions regarding OpenFOAM, like then you can ask me. Like I told you, the important thing is the aim of this lecture section was to get you familiar with OpenFOAM, like what is these things are. What is zero? These are boundary condition and initial condition. These are transport properties and block mesh file. When we run block mesh or mesh, polymesh file is created here. Okay, that is there. And then this system directories. Aim of this session was to get familiar with each and everything. That's why I also told you a little bit about the CFD part. That is every schemes and every solution you can understand why these are there. And apart from that, all these things you can see in like Like whichever command you are giving in this, like block mesh, these are in applications which use source code from SRC files. These kind of things should be clear to you. Then you can like start changing your own code, changing the code of OpenFOAM, or make your own library, or make your own solver will become very easy to you if you are able to understand like how OpenFOAM works. For example, see, you can copy any solver, any basic solver, and modify it to your own solver. Those things you'll be able to appreciate only when you have the overall idea that when we are giving this block mesh file, what are the basic things that are happening. When I'm entering the block mesh file, okay, so it is going to this code, the solver uh, utility, sorry, mesh. And once again, generation block mesh, it is going to this code. It is going to execute the object file or the object file of this code. And how this code will work, this code is dependent upon these files. It has to go to the SRC file and look for these include files as well as these SO files. Like these are the binary code that is already compiled when we run OpenFOAM. Okay, so these kind of things you start with it, you get a hang of it. What are these things? Then you'll be able to juggle with OpenFOAM even inside. You can copy things, paste things, make your own solver.
Abhishek, I think it's beyond 3 hours, so maybe you can ask.
Yeah, I'm asking for questions only right now. Yes. If they have any questions, please let me know.
No, you may ask that whether this extended time is okay or not, because it
Ah,
started
yeah.
late.
One more thing. Previously we used to had the 2 hours workshop, but we are now conducting 3 hours workshop. You guys, you can give your feedback like in WhatsApp group. You can post if it is too long. You want only 2 hours or something like that. Anyway, you'll have these recorded lectures, so you can practice anytime. If you practice all those things, see this again, you'll have not any doubt about the basics of working of OpenFOAM, how OpenFOAM works. You'll have the idea. You have the idea of where the binary files are and how the OpenFOAM actually works, from application to source files to tutorials.
Abhishek, can we see that solver file? Can you open it?
Okay. Any solver file, doc mesh,
Yeah,
I'll
that
open.
the recent problem solver file. How it is the coding is coding
I
pattern.
coding, yeah, we'll cover that, no problem. But I'll just show you. This is in application incompressible. Uh, these both files are there. This is it. This is basically main function in which we are first initially doing something. And this is the rope of icoform, like piezoform. This works on piezoform, similar to piezoform. This is basically piezo algorithm. Sorry, if you
Yeah,
run some
yeah.
piezo.
Instead of piezo, we can also okay simple. You can use that. You are talking about
Transit,
the.
we can use piezo as well as simple both, but
Yeah, yeah.
piezo is more faster. Yes.
That I want to see where actually the code is running. So also
This is the code.
yeah, I can go down little bit. Okay, fine.
So you can have, we'll can also cover those things in later. So just for the introduction.
Yeah, yeah, yeah. I understand.
Okay, everyone, if you don't have any further doubts, so we'll end this session now. So please practice these lectures so that in the next session or in the upcoming weeks, whenever you are like using OpenFOAM, you should be fast enough to catch up. First session is always like that, like this only, that you don't have the idea of Linux-based system, and it takes time to catch up to the new environment of Linux or Ubuntu. So please practice this session. These two cases I have conducted. Please practice those. Change parameters. See like and like debug some errors, and you'll enjoy it. If you have any problem debugging, you are not able to fix the issue, then you can also post in the group. Okay then. Thank you everyone.
Thank you to all for joining this session. Good night, everyone.
I'm stopping the recording.
Yes.
Hello.
Yeah,
Yes, sir.
good night. Good night, everyone.
Good night. Good night.